to fiddle in with some of my slides some more, I think I'm good to go. We don't need the mic, do we? Everyone can use mine. Yep. Cool. All right, introduction to AsyncIO. Before I actually dive into it, a little bit about who I am. Obviously, Nick mentioned I'm the ex-president. I'm in my final semester of a software engineering and maths dual, which unfortunately means I'm at 6th year now. Incredibly sad. I've been a professional Python developer for 3.5 years, and I'm currently working as a freelance consultant. Basically, I'm reading the slides. Haskell is great. Okay, so this talk. So I'm covering AsyncIO, which is a Python library that does asynchronous stuff. This is going to be the structure of the talk. I'm going to start off talking about what concurrency and parallelism are and what asynchronous actually means. I'm going to talk about coroutines. If these words mean nothing to you, you will learn what they mean. Tasks, which is a specific concept in AsyncIO, and then dealing with threads when you're using AsyncIO. And then some fun examples that are not actually that fun, they're just cool. Yeah, this is a Jupyter notebook. If you know what Jupyter notebooks are, they let you do exploratory coding without the along the way. They're very cool. This is my first time ever using one to do a presentation. It could blow up horribly. This is the ultimate live demo. I will be running all code live. So we'll see how that goes. Yeah, feel free to ask your questions throughout the talk. There will be stuff that is confusing. There will be stuff that you need help understanding. If it is too complex to explain concisely, I will say talk to me afterwards because we don't want to be here all evening, especially when pizza's on the way. Brief moment of time. So this is all my Python imports for the talk. We're talking about AsyncIO, so I kind of need that. Types are good, so I want those in there too. Jupyter used to be called IPython, so the module to actually show stuff live is called IPython or display. And then I'll be using requests to get websites for the examples, and I'll be using time to time stuff. And then for the async examples, there is no async request, so I have to use something called AIO HTTP. The last few don't matter, you'll see how they're all used. I'm going to show you that stuff. So, what are concurrency and parallelism? These two are often very easily confused. Concurrency is doing more than one process at once, and parallelism is doing more than one action at once. Now, those are vague words, but here I'm saying a process is made up of multiple actions. And so, when you're doing something in parallel, you're doing two actions at once, like patting your head and rubbing your tummy. And when you're doing them concurrently, it's part of a bigger process. So maybe in order to achieve some other goal, I have to pat my head and rub my tummy. If I'm doing them in parallel, I'm doing them literally at the same time. But the process might not imply that I need to do them at the same time, so I can rub my tummy and then pat my head. So concurrently would be if I was doing those two processes, if I was doing this process that needs me to pat my head and rub my tummy, I instead can rub my tummy twice and then pat my head twice. And that's ticks the boxes for both processes. Hard to understand. Here's a better example. I'm well known for hating Go. It's not that bad a language, I just really dislike it. So Go is known for being good at concurrency, and they've got really good examples. As much as I hate it, it's a really good concurrency example. And so we've got this little guy, this little gopher, and what he's going to do is he's going to burn a bunch of Go programming language manuals. I gotta take it out of Go somehow.
You're not alone in hating Go.
I'm aware. I got a lot of friends on that. So doing it concurrently, and well, the process as a whole is we've got this gopher and he needs to pick up the books, take them to the fire, wait for them to finish burning, and then repeat. So if we're doing this concurrently, the gopher can pick up the books, load them in his cart, take them over to the fire, dump them in, and instead of waiting for them to finish burning, you can go pick up some more books. And so the two actions that are happening at the same time is the books are burning, and the gopher is going to get more books. If we were doing this in parallel, we just get the gopher to bring another friend along to carry more books. They still dump them in the fire individually, they still wait for it to finish and head back individually. but multiple things are happening at once because we've got multiple gophers. So one thing you'll notice here is the gopher itself, like each gopher, when we bring multiple in, can still dump them in the fire, go back and get more books. So you can have concurrency and parallelism at the same time. In fact, you can use parallelism for concurrency. Parallelism almost always implies concurrency, but not the other way around. You can do things concurrently without parallelism. Any questions now? All right, that's either brilliant or terrible. So, synchronous versus asynchronous. When you're doing synchronous programming, you start doing something, you wait for it to finish before moving on to the next thing. If you're doing something asynchronously, you'll start something happening, and if you don't really care about the result immediately, you can go work on something else and come back to it and check when it's done. So with our gopher example, the concurrent process I described was exactly asynchronous. In order for a single gopher to do it concurrently, it has to be asynchronous. Instead of waiting for the books to finish burning, your gopher will throw them in the fire and then go do other stuff. The other useful work is fetching more books instead of waiting for them to finish burning. Yeah, like I said, you can still do the asynchronous stuff in parallel. Parallelism implies nothing about synchronous versus asynchronous. All right, so AsyncIO, the actual topic of this talk. AsyncIO is part of the Python standard library. It was introduced in Python 3.4. In Python 3.5, they added the async and await keywords that make it not horrible to write and not horrible to look at. Python 3.6, they started rewriting some of the Python stuff in C. And in Python 3.7, they completely rewrote the docs. They changed some of the functions in it so that they actually make sense. And generally made it not terrible. It's not amazing, but it's actually good now. So I'll be doing my examples in Python 3.7, although I will be showing you how to do the Python 3.6 version of stuff because it's still super common for people to be using 3.6. But what AsyncIO actually does is it standardizes how async stuff is done in Python land. We had asynchronous libraries before this, specifically gevent and twisted, and there were some others probably, but I've forgotten them, that did mostly this stuff, but they kind of all had different approaches. And AsyncIO provides a standard interface for all of that. So you can actually use twisted or gevent behind the scenes even with AsyncIO. All right. Coroutines. So this is kind of the core building block of any asynchronous programming. Coroutine is short for cooperative routine. It comes from the word subroutine, which basically means a process. That's what subroutine means. With coroutines, you can basically just assume it's going to be a function because it always will be in Python land. But it's something you can, it gets paused and then you can resume. And it's used for a thing called non-preemptive or cooperative multitasking. Come on. There. We've got the dictionary definition of preempt up there. It is take action in order to prevent an anticipated event happening, full stop. That anticipated event in this context would be the continued execution of your function. So we're not doing that. We've got something that can be paused and resumed. Preemptive multitasking usually refers to, in threaded contexts, the operating system will actually stop your code while it's running, switch to another thread, and then stop that one and switch back. So that's something the operating system does when you've got threads and only one core. Cooperative multitasking doesn't require the operating system to intervene. It just says, hey, I'm ready to go. And it gives control back to some scheduler. Yeah, so the Wikipedia definition of preemptive preemption in the computing context with preemptive multitasking is that preemptive multitasking involves the use of an interrupt mechanism which suspends the currently executing process and invokes a scheduler to determine which process should execute next. It doesn't really make it clear what's going on, but good thing is we're not talking about that. Okay, cooperative multitasking. Yeah, instead of being preempted, the coroutine yields control away to whatever's called it. And it's called cooperative because the task chooses to give the control back to the caller. It gets to a point where it's like, yep, I'm all good. You can have a coroutine that's particularly uncooperative and decides to hoggle your CPU and never gives control. You can have something that's like, I'm going to sit here all day long and never give you control, and then once a day I'll give you control. As soon as you give control back to that coroutine, it's still on you. So that's why cooperation is actually important in this context. But the cool thing is, you've probably already seen coroutines in Python. Generators. So with a generator, if you know what they do, they give you something you can iterate over. So they give you output piece by piece. And the way that they do that is when you hit this yield keyword, the result is given back to whatever folder. So we got yield one, and while true. This is just a generator that generates Fibonacci numbers one by one. And in Python, to ask for it to give you a value or to resume the execution until it pauses again, you call next on it, or you iterate over it in a for loop. So let's see what that does. It did stuff, and we can keep going. Oh my goodness. That's the one bad thing about the Jupyter slides. So we've still got the same coroutine object because we got it from up here, but every time we execute it, it continues on. We resume the execution. We've got this thing in an infinite loop, and the only thing that's interrupting is it giving control back to us as the person calling it. Alright. Now we can actually use AsyncIO. Sweet. So this is the synchronous version of me grabbing an image of a dinosaur from the internet and then showing it to you. It's running, it's running. It's not updating. Okay, I'm going to run it there. We got a dinosaur. Ta-da! So all that that's doing is it's getting the dinosaur from the image URL, giving us the content, and then displaying the image. Display image is a function I've predefined that just shows it to us. So we fetch the image, we print out that it's bytes, and we show it. And it does all of that one step after another, just waiting for it to run. The async version looks a little more complicated, but that's just because, yeah, the async version looks a little bit more complicated, and yeah, so we've got the sync version above it. The async version is more complicated because we've got to deal with this client section. It doesn't actually change anything about what's going on, it's just the async library makes us do this if we want to make requests. So where we usually use request.get, we have to use session.get. So let's run that too. And it's not actually running because with that, with that async keyword in front of that, it tells Python we want a coroutine. So at the end, we get a coroutine out. So now we've got generators and async functions both giving us coroutines. So more suspenseful. But how do we actually run an async coroutine? Alright. So at the top, we're calling our coroutine, which says this is the thing that we're going to suspend and resume a bunch. In Python 3.7, the nice version, there's AsyncIO to run. In Python 3.6, you have to deal with this stuff with a loop. A loop is something that can run async coroutines, and so you have to give it to the loop. Or if you're just using your async function inside another async function, you do this await on it. And so what await does is it yields control of the coroutine and says, I'm ready to pause here. Wake me back up when this other one's finished. So it will give control to the loop until, so the loop becomes a scheduler in this context. Give control to the loop until that's done and then resume. So with async coroutines, you personally aren't calling next to control when it stops and starts. You're giving control to this loop that you get from AsyncIO.get. And AsyncIO.run just makes that all easy so you don't have to think about that. Big caveat here. I'm not actually going to be doing that at all. I'm instead going to be doing it this way because Jupyter's cool. I just get to await straight up. because everything in Jupyter is async. So let's run that. That wasn't supposed to happen. Oh, was it? So yeah, this is the code that we had here before, right? That's not how it's actually done. That was a very direct translation to just show you the difference between the sync and the async versions, where you just got that extra client session and that extra read. What's actually going on is the client session does some asynchronous work, and then sending the request does some asynchronous work, and then reading a response does some asynchronous work. And so each one of those is its own coroutine, and so you have to wait for each of those to finish itself. And so we've got this async with, which just converts the with to the I'm doing an async version. When we do the session.get, that sends our request, and we wait for the request to be sent. And then when we do the response.read, that's waiting for the response to be sent to us, and then reading it. So let's actually run it this time. Oh yeah, dinosaur, it's still there, it still works. And you can see that in order to run it, I've again done await here. Alright, so the takeaways from that are async context managers are a thing, and they're slightly different. They just do the stuff async. Async for loops are also a thing. So if you're iterating over something that uses AsyncIO to generate whatever it's giving you, like if you are iterating over something that requests multiple web pages, you can do async for instead. But the main takeaway is you have to write await. Every time something does anything async, you have to write await. And if you're not sure whether or not something is async, you can either try it or read the docs. So yeah, there's a function again. This is important, it's hard to remember. Yes, Will?
Well, that last one where you return from an async function an await variable, could you just return the variable and not the parent await as well?
That's a really good question. So you got to follow the types. Any function that has async at the front of it, you have to await to get the return value out. So if I was to do, you know what, I can get a terminal up. Not Python 3.5, Python 3.7.
Can you make that bigger, please?
Yes, I can. I was just starting up Python, but first. How do I do it?
Make the black bigger.
No. Let's go for like 36 or something.
It's high resolution doesn't stay funny.
Bam. Well, okay. So if we define a function as simple as return 1, when we call it, we still get a coroutine. And we have to await the thing. It says F was never, why does it say F was never awaited? We clearly, oh, the first one was never awaited, that's all. So if we do that again. If we were to return something that is something we would normally have to await, we would instead have to go await, return.
Okay.
Yeah, because you've returned an awaitable that is an awaitable. Yeah, the term awaitable gets referred to, gets used to refer to anything that you can await. Any other questions on? No? Cool. Alright, yeah, you have to write awaitable. How to start stuff. You saw the AsyncIO run again. Oh my goodness. Yeah. So, tasks. All you saw there was doing two things the same way, with one using AsyncIO. Now let's actually do some concurrent stuff. So what we've got here is, we've got a thing that fetches some cats from http.cat, and it shows us the cats. And the way it does it is it loops over the things, and gets the thing, and reads it, and shows it to you. So it's just the same stuff, but I've added this extra stuff here, where we're printing the time. And that's time in seconds. So, let's await that. And that's how we get each cat. So, they came out one by one. Doesn't seem very concurrent. Seems like we're waiting for each one to finish. Let's just... Oh my goodness, what's going on there? That's not even on my screen. Just to be extra sure, let's see how long it takes to pull up. 3.5 seconds. That's not ridiculous. But how do we get it to actually do that concurrently? You got to use a thing called tasks. Wait. Never mind. This is where I'm supposed to lead you astray again. So what if we start the coroutines and then await them all, which is what we're doing here. So what I've done is move the inner bit out into a function instead of being inside the loop. So we're starting fetching the cat, and then we're awaiting them. And it still takes 3.5 seconds. So clearly that's not how you make it go concurrently. What you do need to do is call this create task function. And what that does is it tells AsyncIO, hey, I need to work on this thing here. This one will actually do it concurrently. Gets them all at once, and it takes a total of 2.35 more seconds, which is only slightly more than the one the longest took. So suddenly it's all faster. Yeah, so the only difference between that one and the last one is we are calling create task on all of the coroutines we've pre-created, and then awaiting the tasks. So a task refers to something that AsyncIO knows that it's working on. We've got a coroutine, now we've got tasks. In Python 3.7 it's create task. In 3.6 and below you instead use ensure future. They changed the name because the name didn't actually make sense. Shocking. You'd think that something called ensure future would give you a future, not a task. So that's how you actually do concurrent stuff. You just tell it to start working on the concurrent stuff while you're doing other stuff. All right. It kind of sucks though. Like you have to call create task every time you want to start working on something. Really? Fortunately for simple cases like that, where you're just calling create task on a bunch of stuff, you don't actually have to do it. AsyncIO gives you this function called gather, and what that does is it takes a bunch of coroutines, starts all of them, and then gives you out a list of all the coroutines when they're done. Actually, it's a tuple. Gives you out a tuple where position number 1 is the result of coroutine number 1, and so on and so on and so on. So let's do that as well. And we get the same cats out, and we get the same time being slightly more than the longest one.
There's probably a setting in Jupyter to disable the autosave, right? The autosave.
I had a quick check before we started, and I couldn't find one. What's actually happening is I've got presenter mode up. I might just close presenter mode. Goodbye, presenter mode. Alright, yeah, so AsyncIO.gather makes that simple, I'm calling create task on everything use case a little bit easier. Now, threads. So I'm introducing this as dealing with threading, but it's mainly to try and show you how to wrap stuff so that you can do synchronous libraries but still use AsyncIO. Generally what you want to do is, if you're using a synchronous library that takes a while to do something like a network request or something else, you're going to want to look for an alternative that's implemented straight up with AsyncIO. But it's nice to be able to just automatically do synchronous stuff as well. One great use case for doing the stuff that I'm about to show you is back when we first implemented UQCS bot, it had synchronous and asynchronous stuff. And so the async stuff would all work nicely, and then we just run the synchronous stuff this way. And effectively, the only change that you're going to see here is instead of doing that loop where we're creating all the tasks, we're instead doing this run and executor thing and creating a list of those. So what run and executor does is it takes a thing called an executor and it gives a task to that. And by default, AsyncIO has a thread pool executor. So it's got a bunch of threads and it just gives stuff to work on in threads. Nice and simple. Anything that's synchronous, it just runs in its own thread. You can keep doing AsyncIO stuff, and it lets us know when it's done. That's all there is to it. By passing in a 90 setting, AsyncIO use whatever you feel is good, which is a thread pool executor, and then it runs our synchronous fetch a cat in a separate thread. And it'll fetch all of our cats, but I've actually. So that time is supposed to show that it takes marginally longer. It's really marginal in this case. It's 0.1 of a second longer to use a thread pool executor. With your thread pool executor, there's a bit of overhead in actually spinning up the thread and doing the work to it. So that's especially why. Sorry, it's supposed to be a heat. That's especially why you want to use AsyncIO libraries if possible. And there usually is one. So this is basically, this run and executor is essentially the #1 easy way to wrap a non-async library in AsyncIO stuff. Yes?
Is it a bad way to split work because it still have guild problems?
Yeah, so for those that don't know, Python has a thing called the GIL, or the Global Interpreter Lock. It means that only one computer thread can execute Python code at a given time. Which means that basically if you try and use threads for parallel stuff, they suck because you're still only running one thread at a time, but with the overhead switching between threads. And yes, Will, that does still apply here. You generally don't really use AsyncIO for high CPU load. It's really good for high I/O throughput. That's the killer application of it. But there is a nice big exception because Python has more than one executor. So the default is a thread pool executor, but there's also a process pool executor. And executors have been provided in Python since back in Python 2 by the concurrent.futures module. So thread pool executor spins up a bunch of threads and gives the work to them. Process pool executor spins up a bunch of brand new Python processes and gives the work to those. And so it's the standard solution to Python and the GIL is instead of using more threads, use more Python processes. But concurrent.futures also provides an abstract executor that you can extend yourself. And it relies around the concept of futures, which is AsyncIO building block number 3. We've got coroutines, we've got tasks, and now we have futures, which is why the poorly named ensure future function existed. So that's what a future looks like. I haven't actually got the implementation there because it's entirely irrelevant and provided by Python, but those are all the functions on it. If you're familiar with JavaScript, you'll be used to a promise. A future is a lot like a promise. Python futures are futures versus tasks. There's a lot of overlap with JavaScript promises. JavaScript is kind of combining tasks and futures in one, whereas in Python, futures are something else. A future is just tracking that here is something that's working that will eventually be a value. It doesn't care about what the thing that's working is. It just is the marker that says when it's done, you'll be able to tell that it's done here. And in AsyncIO, they're used as a bridge between low-level implementations of AsyncIO libraries where we've got synchronous code and you want to make it asynchronous. So I do have a little example here. Is it on the same slide? No, it's not. All right, I'll go explain some stuff. Yeah, so a future can be running. Yeah.
Couldn't you also argue that there's also a lot of overlap between a future and a coroutine as well?
Not Python land. And so in JS land, there's the overlap between task and future in Python and promise in JS. You kind of get slightly distracted by that in JS land because the .NET on promises is such a nice clean API that it makes it almost seem like coroutines, when in fact you've just got a bunch of change functions. If you use async await in JavaScript, it's exactly the same as async await in Python though. Yeah, so a future can be running, cancelled, done with a result or done with an error. And so you've got a status thing that says, hey, I'm running, hey, I'm cancelled, hey, I'm done, and I want the result, and I'm going to wait for it, or I want the error, and I'm going to wait for it. And if either of those return none, there is none. And then you can add a callback that says, call me when I'm done. So it allows you to chain functions together with the futures, which is how part of the overlap with Python works. And then the last three are used when you're actually implementing something using futures. If you're doing something low level, when you're doing the stuff, you can then on the future say, hi, I've started running this, let me know if I'm already cancelled. Hi, I'm finished, here's the result. Or hi, I'm finished, here's the error. And these report back to anything that's waiting on it. So it's just a marker that lets you say, from one end, I'm done, and from the other end, wait for it to finish. So AsyncIO can directly use futures. All you have to do is call AsyncIO.wrap future on it. Yes, there is an assure future and wrap future. That is why Python 3.7 is better. So this example here is just a work queue. And if you put into the queue that, hey, I've got this future and I want to call this function with these arguments and these keyword arguments, it will then do all the stuff that's needed for a future. So it will check whether, it'll say, hey, I'm running, and it'll check if it's cancelled. And if it is cancelled, it'll go to the next one. If it's not cancelled, it'll try and call the function and save the result. If we get an error, we'll set the error and go to the next one. And if we get a result, we'll set the result and we finish and go to the next task. So that's how you would use the futures API if you were implementing it well. And then I went to start implementing Executor and forgot that I did not finish. So there is that.
Can you run past line 2?
Line 2.
It's a 4.
So iter is a function that's built in by default. Iter takes something that you can iterate over, and if you give it a second argument, it will iterate over the thing until that argument rocks up. So what this is actually doing is it's going to pull everything off the queue until we get none on the queue. Yeah. So, are there any questions on anything you've seen so far before I go into examples that will get quite complex dramatically quickly, but start off really simple? No questions? I'm assuming that's a good thing. Yeah, so I've got 3 examples for you, and I'm happy to go through any other stuff on the command line. Number 1 is a web app using AsyncIO and a library called Sanic. Sanic is actually absurdly fast, hence the name. It is one of the fastest web servers you'll see. It can outperform Node in some situations and can outperform Go in some situations. And part of that is because it uses a thing called UV loop underneath it. UV loop takes the event loop from Node.js and then puts it in Python land. And essentially, if you're writing AsyncIO and you're not on Windows, you want to be using UV loop, because all you have to do is install it, and then it takes 2 lines of code, and suddenly everything AsyncIO was insanely fast and really good. And it's driven a lot of the hype behind AsyncIO. Example 2 is a TCP echo server. If you don't know what TCP is, basically it's accepting a web connection, it gets a single message, and it spits that message straight back out to the person who sent it and stops. And then example 3 is the nice big complex one. This is something I actually did at work. Kafka is a distributed message queue, and there's a really, really good, efficient library for Python. But it's all completely synchronous. And so I had to wrap that in AsyncIO for some work we were doing. And so it's the full implementation of a Kafka producer, so something that spits stuff onto the message queue, using the synchronous API to generate an AsyncIO API. All right, this is a web app using Sanic. That's the whole web app. If you hit the root endpoint, it spits back the text, I'm a teapot, with the status code 418, which is the status code for I'm a teapot, and then it stops. And it does it really, really fast, because it's using AsyncIO and it's using Sanic. I'm hoping there's no questions about that one. If you've used Flask before, Sanic is incredibly similar to Flask. The API is almost the same, you just pass request in as a parameter to the function, rather than having it as a weird module variable thing. Sanic's really cool, Sanic's really good, you should check it out. If you're building a web app in Python, just use it because it's fast. So this is the TCP echo server. This one's taken straight from the Python docs. And the main reason I'm showing you this is to show that AsyncIO has this stream reader and stream writer API that allows you to deal with network connections as just a stream that you read from. So here we are waiting for the reader to give us some data. Then we do some processing on it. That writer.get extra info is just a normal function on it. You don't need to await it or anything. So you can, the mixing of synchronous and asynchronous code goes on here. We then write the data to the writer. All that's saying is, hey, I want this data to eventually be written. This await writer.drain actually makes sure all the data has been sent from the buffer and is sent to whoever you're waiting on. And then it closes. And to actually run that, all you have to do is use asyncio.startServer, give it a host and a port, and it does all the stuff for you. And then when you want the server to close, the server closes. That's it. That's a TCP server. Any questions on that one?
How much faster is it versus a dumb solution?
Depends how dumb your dumb solution is. So, if you're using the stream reader and stream writer API to do a TCP echo server and you're using UV loop, it's absurdly fast and you'll get like 2 times C performance, which is pretty good. If you're using the normal AsyncIO without UV loop, you're looking at 10 times C performance. The big difference is when you've got multiple connections happening at once, the throughput stays just as good. So it's not any faster to run the actual Python code that's going on. It's just every single time when you give control back to AsyncIO, it has the opportunity to run something else. And so you can run a lot more stuff all at once. It just so happens that UV loop is also absurdly fast, and so it does speed some stuff up. So the main reason you want to use AsyncIO is for concurrent workloads. But if you have simple network stuff, UV loop does make it absurdly fast, and so it's still a good use case there. Yeah, any more questions on that one? Or questions more general?
How do you spell
UV. Yeah, it's built on libuv, which is the C library for the node event loop. And here's my favorite and most complicated one. Wait, there. Oh my goodness. Wait up. W, isn't it? Yeah, these are cool, but they're also a huge hassle. There we are. All right, this one's a bit of a stuff around. So the way that this works is, this Kafka producer works is, when you want to send a message, you call .produce on it, and that doesn't actually send the message. That puts it in a queue to be sent. And in the background, the library that's running all of this code actually has a bunch of C threads that are doing all the work to send it. But you don't actually get told it's done sending until you call this poll function, which gets called in poll loop. So step one of doing the async producer is I have to make sure poll gets called somehow. And AsyncIO at its lowest level is built on callbacks. And so if you've ever written JS, you'll know set timeout and set timeout with an argument of 0. AsyncIO has equivalents of those. They've got loop.callSoon and loop.callLater. So when we first create our producer, we start this loop that polls every now and then using this callback feature. So loop.callSoon calls our poll loop as soon as AsyncIO has control again. And then when it calls that, we get the loop, we do the poll call. So the 0 argument is a timeout and just says, hey, I'm not going to wait for anything, just tell me everything that's already done. And then we then do loop.callLater, and we call the poll loop again in 1 second. So it's kind of recursive, but it's far enough away that we don't get into Stack Overflow issues. The reason we have this poll handle here is Python and AsyncIO has this weird thing where if your task gets garbage collected while it's yet to happen, it can just not get run. I ran into an issue where I had a semaphore that was constraining how many tasks of mine could run at a single time. And once you hit the limit, nothing happened because all of them were getting garbage collected before they finished. So we couldn't actually release the semaphore, things just got stuck. So you have to hold a strong reference to your tasks. But yeah, so what poll does is it triggers all of the callbacks you give when you pass things as produced. And so we've then got this thing called send, where we want to wait for the sending to finish. And what that one's doing is it's creating a future for us. So the future API I said before, where we're bridging the low level and the high level async code. We've then got this function that will, when the message is delivered, call our send callback, which is this thing here, with the future as an argument, as well as whether or not there was an error and what the message was. So we'll then call produce, which gives it to the queue, sends it to the given topic with the given message, and on delivery, we want our callback to be called. And then we call poll as soon as possible after that. The reason for calling poll as soon as possible after that is just if you're interacting with the thing, you may as well trigger a poll while you're there. It means that you get feedback back faster if you have more stuff going on, which is a weird thing. We've got this performance issue where, oh, it looks like everything's taking longer because we're not getting our callbacks triggered because we've suddenly reduced the volume of requests. And then when the volume of requests went back up, everything seemed faster again, which is counterintuitive. And it's because of this extra poll call here, was that things that were waiting to be triggered by the next one in our loop were getting triggered when we next did a send, which was kind of cool and not at all intuitive. But anyway, so produce queues that up, the threads in the background do their work. When it's done and someone calls poll, then these callbacks get called. And we've got our future that we passed in down here, and we set our exception, we'll set our result. And that tells AsyncIO, hey, I'm done, and here's the result. And the wait finishes. And then when we're all done, it just stops looping, and that's it. So there's a lot going on there. But it's remarkably little code to do this really high performance bridge between this low level synchronous library and the asynchronous code. That one's a lot to unpack. If you have any questions, feel free. All right, cool. You have to do the black screen button. It doesn't work. What? There's a black screen button and it's not working. Come on.
Is this just built into Jupyter or is it?
No, it's an extension. Yeah, so that's the talk.